Let's continue with proposition 21. If on one of the sides of a triangle, from its extremities, there be constructed two straight lines meeting within the triangle, the straight lines so constructed will be less than the remaining two sides of the triangle, but will contain a greater angle. Sounds complicated, but let's diagram this out. So what's going on here is we have our triangle ABC. A, B, and C. And he says, on BC, one of the sides of the triangle ABC, from its extremities, B and C, let the two straight lines BD and DC be constructed meeting within the triangle. So what's going on here is we have some other point, which we're going to call D within the triangle. And we're going to connect DC and DB. And we notice that there's a smaller triangle, DBC, within the larger one. I say that BD and DC are less than the remaining two sides of the triangle, namely BA and AC, but contain an angle BDC greater than the angle BAC. So what he's saying is that if we form this smaller triangle here within the larger one, then BD and DC taken together will be lesser than BA and AC taken together, but this angle in here is going to be larger than this one up here. So there's two claims to prove. The first one about the pairs of sides, and the second one about the relationship between these two angles. And he says, first, for let BD be drawn through to E. So what's going on here is we have a point E. And to form that, we're simply going to extend BD over to E. Then, since in any triangle, two sides are greater than the remaining one, therefore in the triangle ABE, that's this one over here, ABE, the two sides AB, that's this one here, AB, and AE are greater than BE. So to highlight this, saying that BA and AE are going to be greater than BE. And that's true by proposition 20, the triangle inequality. He then says, let EC be added to each. So what happens if you take those and add EC to each one? Remember, we had B to A and A to E, but now we're going to add E to C. And you can now see it's B to A and A to C. So on the one hand, we have that. Whereas on the other, we have B to E and E to C. Therefore, what we can say is that BA and AC are greater than BE and EC. So we've seen this relationship that BA and AC taken together are going to be greater than BE and EC taken together, which follows straightforwardly from the triangle inequality, proposition number 20. And then we're going to reason a little bit about the triangle CED. That's this one over here, CED. And let's highlight the sides that he's talking about. The two sides CE and ED, so which are those? That's CE and ED, are going to be greater than CD, which is, of course, true. That's just another application of proposition 20. But then he says, we're going to let DB be added to each. So let's check this out. So we have CE and ED, but then we're going to add DB. So now notice we have CE and EB. But then on the other hand, recall we had CD, and now we're going to add DB to that. And from that, it follows, we'll write down what follows from that, that CE and EB are greater than CD and DB. just to make sure that's clear, we're saying that CE and EB are greater than CD and DB. Just an application of the triangle inequality. But then he says, recall that BA and AC were proved greater than BE and EC. But now notice that the same pair, CE and EB, is greater than CD and DB, from which it follows that therefore BA and AC are much greater than BD, BD, and DC. But notice what those pairs are in the triangle. On the one hand, BA and AC. So BA and AC, we've just proved that those two taken together, are greater than BD and DC taken together, which is just what we aim to prove, at least for the first part. That's the first claim proved. Now we have to prove that claim about the two angles. Now for the second part of the proof, we're going to prove that BDC is greater than BAC. So we continue. Again, since in any triangle, the exterior angle is greater than the interior and opposite angle by proposition 16, therefore in the triangle CDE, that's this one over here, CDE, the exterior angle BDC, so where's that? That's BDC, is greater than the angle CED, which is this one, which is of course true by proposition 16. So let's record that, the relationships between those. So we have that BDC is greater than CED. Now, if we check out the triangle ABE, as he says, for the same reason, moreover, in the triangle ABE also, the exterior angle CEB, or CEB, that's once again this one, is greater than the angle BAC. Just another application of proposition 16, that the exterior angle is greater than the opposite and interior angles. So let's record what we've learned from that. Also notice that that's the same angle as CEB, CED. So what we've learned is that CAB ranks lower than this, or BAC, same thing. But the angle BDC was proved greater than the angle CEB. Therefore, the angle BDC, where's BDC? That's this one. This must be much greater than BAC, which is what we set out to prove. And just to reiterate what he says, we've said that the angle BDC is greater than this opposite and interior angle, which was CED, also CEB, but that very same angle must be greater than this opposite and interior angle. Therefore, this angle must be greater than this one.